Good morning, good afternoon, and good evening, everyone. Welcome to another RTDS Technologies webinar. My name is Katie Sidwell, and I'm our Technical Marketing Manager at RTDS, and I'm happy to be your host and moderator today as we talk about empowering hydrogen energy with real-time simulation and HIL testing of multi-energy systems. So I'm going to start with some housekeeping notes, and then we'll get right into our program. I'm not going to talk for very long today. I'll be turning it over to my colleague Janesh Rupasinghe, who is a simulation engineer with RTDS, specializing in hydrogen and multi-energy systems modeling. So Janesh will start by taking you through some background on multi-energy flow simulation, talking about the motivation for developing these sample cases and components for the RTDS simulator. He will review our hydrogen system models. So we have quite a few newer components available for modeling different aspects of hydrogen plants. So he'll take you through the available components and some of the modeling theory as well. And then he will switch to a screen share and do some case demonstration in the RSCAD FX software. As usual, we will have a live Q&A session at the end of the webinar. As you come up with questions throughout the presentation, please feel free to submit them in the Q&A widget. So we will be answering your questions as we go through the presentation. So if you have a question early on, please feel free to submit it right away. And then we'll go into some deeper discussion on some of the question points at the end. As always, we are recording this webinar and it will be available as a recording for you to access on demand or pass on to other colleagues. So if a colleague wasn't able to attend today, they can still visit the webinar page, register themselves, and watch this webinar on demand. One important note for today, if it is your first time joining us, or if you're new to our technology, we are not doing a general primer on the technology today. So if you'd like to learn more about real-time simulation and hardware-in-the-loop testing fundamentals, please head to our YouTube channel and check out our more introductory videos there. We're doing a little bit more of an applications deep dive today. And if you're not familiar with us, we are headquartered in Winnipeg, Manitoba, Canada, where we've got plenty of snow and cold at the moment. And we pioneered real-time power system simulation in the 1980s. So we developed the RTDS simulator, which is now the industry standard for real-time simulation and closed-loop testing. It's used by utilities, transmission and distribution system operators, manufacturers of protection and control equipment, research and educational institutions, and consultants worldwide. Our tool is increasingly used for de-risking grid modernization and validating novel technologies prior to their integration on the grid. So it's very apt when it comes to hydrogen and multi-energy systems like we're discussing today. Just before we move on to the presentation, I want to let you know about an exciting event we have coming up. It's our 2025 North American Applications and Technology Conference. So it's happening May 6th to 8th in Chicago. And this is a great opportunity to connect with RTDS users. Whether you are an existing user or if you are potentially looking at the technology to apply to a project, you can connect with others and learn more about newer applications of the tool. And we'll also have RTDS staff there presenting on some of our newer features, like our frequency scan tool. There will be a great tour of ComEd's state-of-the-art grid integration and technology laboratory. So that's what you see in the photo here. They have quite a large RTDS simulator setup that they use for a wide variety of automation projects, including microgrids. So that should be really interesting. And again, everyone is welcome at this event. It's not limited to customers located in North America. It's free to register, so you can visit this link if you're interested in registering as an attendee or submitting a presentation topic. And at the end of the webinar, you'll be redirected to this page as well, so you can bookmark it or send it to a colleague. Okay, without further ado, here is Janesh on hydrogen and multi-energy.
Thank you, Kathy. Hello and welcome everyone. Thank you for joining today's webinar. I'm Janesh from RTDS Technologies, and I am excited to present the webinar Empowering Hydrogen Energy with Real-Time Simulation and Hardware-in-the-Loop Testing of Multi-Energy Systems. This is the agenda of this presentation. I will begin with an overview of hydrogen energy and multi-energy system, providing basic knowledge for those new to the topic. Then I will introduce the new hydrogen energy component we developed in RSCAD. Next, I am going to discuss practical application of these simulations in real-world scenarios. At the end of the presentation, I am going to conduct a demonstration showcasing the simulation capabilities of these new hydrogen multi-energy simulation components. Finally, we can come to the Q&A session. Hydrogen energy refers to the energy we derive from hydrogen gas. Because of several potentials shown by the hydrogen gas, it is identified as one of the best energy carriers for the future. They have many advantages such as eco-friendliness. If used in the right way, hydrogen does not emit any greenhouse gas, making it an environmentally friendly option. They have a very good conversion efficiency, up to 60%. Considering other benefits of hydrogen, this is relatively a high value. Hydrogen can be used to store, transport and deliver energy produced by other sources such as renewable, providing the versatility. Due to these benefits, the role of hydrogen in power system is becoming more important. They provide new opportunities for energy storage and grid balancing. However, because of the early stage of the development, they face several limitations. The main limitation is the lack of efficient and diverse hydrogen production technologies. Eco-friendly methods such as electrolysis are available, but they are not available in large scale. Another limitation is the lack of efficient and cheap storage mechanism. Hydrogen gas has a low volumetric density, making it difficult to store. Hydrogen-based energy converting devices almost always need the power electronic interface to connect to an electrical system. This setup leads to problems such as harmonic, current ripples, efficiency issues, and switching losses. Overcoming this limitation needs a lot of research and studies. To help with this, we have introduced an advanced hydrogen multi-energy flow simulation facility in RTDS. Let's take a look at multi-energy systems. A multi-energy system integrates various types of energy sources such as electricity, heat, and hydrogen, and they optimize how we generate, store, and use energy in an organized and flexible manner. There are few core components to a multi-energy system. First, we have the energy sources, for example, renewables and storage systems such as batteries and hydrogen. Then we have energy conversion system that can transform one form of energy into another. Finally, we have energy distribution network that transmit and distribute energy across different sectors such as power grid, heating network, and hydrogen network. The benefit of multi-energy systems are significant. They can improve energy efficiency by optimizing different energy sources. They can enhance stability by providing the flexibility. They can also help to reduce the cost by using the most appropriate energy source at a given time. They can increase energy security by diversifying the energy mix. Also, multi-energy systems enable advanced energy storage solutions such as hydrogen. Now let's look at how hydrogen integrates into multi-energy systems in RTDS. In RTDS, we typically focus on power system application or electrical energy aspects. However, in hydrogen energy system, we have not just electrical aspect but also thermal and hydraulic parts. The multi-energy flow component in RSCAD can simulate electrical behavior as well as the thermohydraulic behaviors of actual devices. For this, we have modeled several energy conversion devices. Also, we have several secondary components to support the functionality of these energy conversion devices. All the energy conversion devices are modeled as power system component in RSCAD. They are interfaced with the electrical network using their equivalent circuit. All the secondary components are modeled as control components. These components are designed to enable multi-energy flow simulation by handling 4 types of components. They are hydrogen, oxygen, nitrogen, and water. For hydrogen, oxygen, and nitrogen, we assume the ideal gas behavior. For water, we assume that it can exist in both gas and liquid phases. The thermodynamic properties of these compounds are calculated using polynomials, which are defined for a specific temperature range as shown in this table. In this slide, you can see the models we currently have in our multi-energy flow library for hydrogen system simulations. We have 3 energy conversion devices which are modeled as power system components. They are proton exchange membrane or PEM fuel cell stack, PEM electrolyzer stack, alkaline electrolyzer stack, which is the most mature electrolyzer technology. Then we have secondary components such as storage tank, the gas compressor, fluid mixture, and the fluid property calculator. In the simulation of hydrogen energy systems in RTDS, individual components are modeled separately and they are interconnected to form a flow-based system. Each component consists of ports to provide pressure, temperature, and molar flow rate of the input and output flows. Apart from that, they require to specify the molar fraction of all 4 compounds in the flow. Those are hydrogen, oxygen, nitrogen, and water molar fractions. When connecting the output flow of one component to the input flow of the next component to form the flow, typically there are 7 variables that need to be connected. First, we have to connect the pressure, temperature, and the flow rate of the first component to the input of the second component using wires or wire labels. Then molar fraction of output flow compounds from the first component must be given to the input of the next component. This can be done using the same signal name. Now I am going to discuss each component individually. In this webinar, we are going to focus on the general aspects and features of each model and will not discuss the mathematical aspects. Now I am going to discuss each component individually. In this webinar, we are going to focus on the general aspects and features of each model and will not discuss the mathematical aspects. The first component is the PEM fuel cell model. The basic structure of a single fuel cell is shown in this figure. It consists of an anode, cathode, and electrolyte membrane. Hydrogen is provided to the anode as the fuel. Oxygen or compressed air is provided to the cathode. A reaction takes place inside the anode, decompose incoming hydrogen into proton and electron. The electrolyte membrane has a low resistance to positive ions, hence it allows proton to pass through to the cathode side, and it also blocks electron from crossing. As a result, electrons are passed through an external circuit, creating a direct current from cathode to anode. We can connect a load in between the anode and cathode to get the power to the load. Cathode undergoes another catalytic reaction that allows oxygen to combine with incoming protons and electrons to produce water. In our RTDS model, you can connect a number of cells in series to achieve a desired voltage and a number of stacks in parallel to achieve the desired power. This fuel cell represents its voltage using the equivalent circuit shown in this figure. It consists of 4 key voltage components. First we have the reversible voltage, which is modeled as an ideal voltage source. Then there are three types of voltage losses that are modeled as resistances. The actuation loss account for the energy required to drive the electrochemical reaction in the cell. Then the concentration loss represents the voltage drop due to the reactant depletion at the electrodes. Finally, ohmic loss resistance captures the resistance from membrane, electrodes and other internal components inside the fuel cell. This model also includes several key features. It accounts for hydrogen and oxygen supply and utilization, ensuring proper mass dynamics. It can simulate fuel starvation, which helps to assess system performance under low fuel conditions. This model also tracks anode and cathode pressure, which are derived using ideal gas laws. Membrane water content is another important factor, as hydration of the membrane affects the conductivity and the overall performance of the fuel cell. Finally, the model includes stack temperature dynamics and a cooling system to manage the temperature inside the stack. To evaluate the performance of a fuel cell, it is important to understand the characteristic curve of the cell. We can answer a lot of questions related to the fuel cell simulation using these curves. In blue color, you can see the polarization curve of the fuel cell, which displays the voltage output of the fuel cell for a given current density loading. Then in red color, we can see the power density curve, which gives the power delivered by a unit area of the fuel cell as a function of the current density. Based on its behavior, the polarization curve can be divided into several regions. Point A represents the reversible voltage of the fuel cell, which is approximately 1.2 volts. Point B represents the open circuit voltage of the fuel cell. It has an open circuit loss due to the undesired fuel crossing through the membrane of the cell. Then the rest of the curve can be divided into three regions. First, we have the region of activation polarization. As the name implies, the losses in this region are dominated by the activation losses. Then we have a linear region, which is referred to as the region of ohmic polarization. Finally, we have the region of concentration polarization. Generally, a fuel cell operates in the linear region of the curve. The typical operating voltage for a single PEM fuel cell varies between 0.6 volts and 0.7 volts. In this slide, you can see the PEM electrolyzer model. Electrolysis has the opposite of the fuel cell operation. In this technology, an electrical DC power source is connected between the two electrodes, and water is given to the anode of the cell. Inside the anode, water is decomposed into proton and electrons while generating oxygen gas. The proton pass through the membrane to the cathode side, while electrons are forced through the external circuit by the voltage difference of the source. In the cathode, incoming proton and electron are recombined to produce hydrogen gas. Generated oxygen and hydrogen gases leave the electrolyzer and can be used in other applications. PEM electrolyzer has the same equivalent circuit as the fuel cell. However, because the current flows in the opposite direction, the voltage components add up to the reversible voltage component of the cell. For this model, we assume the membrane is fully hydrated because water is continuously supplied to the electrolysis cell. The water consumption inside the cell is directly proportional to the current of the cell, and it is modeled using this equation. Thermodynamic behavior and the individual components are calculated similar to the fuel cell model. As you can see from the figure, similar to the fuel cell model, electrolysis cell polarization curve can be divided into three regions based on which our potential is dominating. Now each voltage component is adding up to the reversible voltage. Therefore, the operating voltage of the cell is much above the reversible voltage. Typical operating voltage range for PEM type electrolysis cell is 1.6 volt to 2 volts, and current density vary from 0.6 to 2 ampere per square centimeter. This is the alkaline water electrolyzer model. It is a much mature technology compared to the PEM technology. In this process, two electrodes are immersed in the electrolyte solution of potassium hydroxide or sodium hydroxide. DC power supply is provided between two electrodes and a continuous supply of water mixed with potassium hydroxide or sodium hydroxide is supplied to the cell. In the cathode, water molecules react with the incoming electrons from the anode, generating hydrogen gas and hydroxide ions. The electrolyte solution acts as a conduction pathway for the hydroxide ion as they go through the diaphragm to the anode side. At the anode, the hydroxide ion decomposes into oxygen and water while releasing electrons. Finally, the electrons are forced to the cathode side through the external circuit by the voltage difference of the connected DC power supply, creating a current from cathode to the anode. The draft component, the equivalent circuit and the characteristic curve of the alkaline water electrolyzers are shown in the figures. The model has similar features to the PEM electrolyzer with some minor changes. Since alkaline technology operate in relatively lower current densities compared to the PEM type, the mass transportation loss is ignored in this model. The model is designed to facilitate both potassium hydroxide and sodium hydroxide electrolyte types. Draft component, equivalent circuit and the characteristic curve of the alkaline water electrolyzer are shown in this slide. This model has similar features to the PEM electrolyzer with some minor modifications. Since alkaline water electrolyzer operate in relatively lower current densities compared to the PEM type, mass transportation inside the model are ignored. This model is designed to facilitate both potassium hydroxide and sodium hydroxide electrolyte types. Compressed gas is the most well-established hydrogen storage technology. Therefore, the storage tank model in RSCAD is developed to represent the behavior of a storage unit that can hold or supply compressed gases. It supports three thermodynamic operation modes. They are isothermal, adiabatic and generic. Isothermal means the temperature inside the tank is a constant. Adiabatic means that there is no heat transfer with the environment. And the generic mode is a non-adiabatic and non-isothermal mode. Calculation of the internal state of the tank is different for each model. The model can fully simulate the dynamic of internal variables such as pressure, temperature and mass of the storage gases. Calculation of some internal variables require iterative algorithm. Therefore, this model sometimes is expensive. Next component is the gas compressor model. Compressor's task is to deliver a gas at a desired rate and a desired pressure by performing work on the input gas. Therefore, it consumes a certain amount of mechanical energy. Mass flow dynamic inside the compressor is characterized by a first-order transfer function with the user-specified time constant, as shown in this figure. User has the flexibility to choose the compression process between isentropic and polytropic processes. Flow mixture is another auxiliary component needed in the hydrogen system simulation. Task of this component is to calculate the thermodynamic properties after mixing two fluids. It accepts two fluids and calculates the final molar flow rate, temperature and pressure and the molar fraction of the mixture assuming there is no chemical reaction take place due to the mixing. For this model as well, iteration algorithms are used to compute some parameters. Last component is the fluid property calculator. This component can use to monitor thermodynamic properties such as enthalpy, entropy, heat capacity, Gibbs energy, mass flow rate, and water vapor fraction of a fluid flow between components. This component can also be used to convert mass flow rate to molar flow rates. Now let's have a look at the application of the hydrogen simulation models. Now let's have a look at application of the hydrogen simulation models. This slide highlights some key hardware-in-the-loop application of the new hydrogen multi-energy simulation facility. One major focus is testing control system of hydrogen systems. Using these models, we can test fuel supply controllers including hydrogen and oxygen delivery, ensuring proper flow and response under different conditions. We can also test water supply and hydrogen production controls, which are critical for electrolyzer and fuel cell operations. Another key aspect is membrane humidity control. Since fuel cell membranes need the right moisture level to function efficiently, we can test how control strategies can manage humidity in real time. Temperature and coolant flow control are also essential, and our models allow us to assess how well these systems can maintain operating conditions. On the safety side, our models can help to test and validate fault detection and emergency shutdown protocols. These models can simulate conditions such as fuel starvation and low membrane moisture to verify that safety system can detect and respond appropriately to those situations. Users can evaluate safety mechanism under extreme conditions such as overpressure and overheating conditions. Then they can observe their shutdown protocols. This model can also be used to validate pressure regulation system for hydrogen gas storage, which is critical for maintaining safety and efficiency in storage and distribution. Beyond control and safety testing, these models support a range of other hydrogen energy applications. This model can be used to determine optimum operating condition under varying loads, temperatures, and environmental factors. Using these models, we can investigate how hydrogen systems interact with renewables and the power grid, ensuring seamless integrations. We can simulate power to hydrogen systems. The library enables the evaluation of hydrogen production as a means of storing surplus renewable energy for later use. It also allows modeling of scenarios where hydrogen systems supply energy back to the grid, which are referred to as bidirectional energy flow. Then we can evaluate the dynamic response of hydrogen systems under shifting grid demands and frequency variations. Using this facility, we can validate new system design and configuration before they are implemented in real world. These capabilities makes our simulation facility a key tool in advancing hydrogen energy and its integration into the modern grid. That concludes my presentation. Now I am going to start the demonstration in RSCAD. Now I have switched over to RSCAD software. First I am going to demonstrate a simple power to hydrogen system simulation. Before proceeding to the case, I want to show you how to get the characteristic curve of the electrolyzer. In this case, as you can see, I have placed number of electrolyzers on the graph. The goal here is to get the characteristic curve for the electrolyzer for different pressures and different temperatures, while keeping all other parameters the same. This kind of analysis is going to be useful in determining operating condition for electrolyzers, which you are going to use in your simulation case. This is the first or the reference electrolyzer. For this particular stack, I have used 353 Kelvin, which is equal to 80 degrees of Celsius as its temperature. And for the pressure, I have used 100,000 Pascal, which is equal to 1 bar. All the stack and cell parameters are set using draft variable, which are placed at the top of this draft case. For all the electrolyzers, I have used the constant temperature mode, which means the temperature dynamic inside the stack is ignored. In order to provide the voltage to the electrolyzer, I use this control voltage source. The source voltage is set using this external control logic. When I press the push button, it is going to change the voltage from DC minimum to the DC maximum. A rate limiter placed here makes sure that the voltage change is gradual. If I roll down, for top 5 electrolyzers, I change the operating temperature from 70 degrees of Celsius to 30 degrees of Celsius. So while I am changing temperature, I keep all the other parameters the same, including the pressure. For the bottom 5, I change the operating pressure while keeping everything else constant. Now let's look at the characteristic curves in runtime. In the runtime, I have placed sliders to change the minimum and maximum DC voltage, a push button to get a plot update, and again sliders to change the stack parameters, top row electrolyzer temperature values, and bottom row electrolyzer pressure values. Then I have two XY plots to draw cell voltage against current density for each electrolyzer. Now I am going to run the simulation. Once the simulation starts, I can press this push button to trigger a plot update, and then it takes about 10 seconds to give you results. Since hydrogen production is directly proportional to the current, the electrolyzer that requires the lowest voltage for a given current density has the best performance. Keeping that in mind, you can see that highest temperature, which is the 80 degrees of Celsius, has the best performance, and the curve related to the lowest temperature, which is 30 degrees of Celsius, has the worst performance. This is due to the temperature in stack increase the electrokinetic of molecules, reducing the electrical energy requirement for the chemical reaction. If I go to the second graph, you can see that increase in cell pressure results in an increase in cell operating voltage. For example, for 1 bar, you can see the best performance. The top curve is related to the highest pressure, 50 bar. This means higher the pressure, the performance of the cell is less. However, in real world application, typically higher pressures are used due to less compression state requirement after the electrolyzer before storing. It increases the efficiency. Now let's have a look at the simulation case of the electrolyzer. In this case, I am going to simulate a simple grid connected power to hydrogen system using an alkaline water electrolyzer. Since they typically operate with high current and low DC voltages, rectifiers based on thyristor converters are used as the interface between the electrolyzer and the grid. Inside this hierarchy box, I have the LCC controller. The task of the controller is to supply a controlled DC current to the electrolyzer to produce hydrogen at a desired rate. Since hydrogen production rate is directly proportional to the electrolyzer current, you can either choose to control the electrolyzer current or the hydrogen production rate to generate the firing angle to the thyristor bridge. If I go inside this green color hierarchy box, I have the electrolyzer and the hydrogen storage tank. Input to the electrolyzer are the water flow and the coolant flow, which are given using these input ports. Output of the cathode and the anode are given separately. Typically, anode output contains oxygen gas and the cathode output consists of hydrogen gas. Therefore, as you can see, the cathode output is connected to the storage tank to store hydrogen gas for later use. Electrolyzer system also consists of a water controller and a temperature controller, as you can see here. The water controller's task is to ensure a continuous water supply to meet the hydrogen demand of the electrolyzer. In this controller, the water requirement is computed based on the current reference from the converter and a utilization factor, which is given here. The utilization factor is the ratio between the water utilization and the water supply. This is the temperature controller. It adjusts the coolant flow rate to the alkaline water electrolyzer stack to maintain its temperature at the desired value. So I am controlling the temperature at 350 in this case. Now we can go to the runtime. In the runtime, you can see graphic to depict the system. Sliders to change the stack and control parameters are placed inside this hierarchy box. Users can change these sliders based on their system setting. Inside this hierarchy box, the yellow color one, I have placed graphics and numeric meters to observe some important variables of the alkaline water electrolyzer and the hydrogen tank. The stack pressure The stack temperature is controlled at 350 Kelvin and the hydrogen production rate is set to 1 per unit. Now I am going to start the simulation. After starting the simulation, I am going to follow the startup sequence given here. First, I am going to enable the water supply to the electrolyzer. Then I am going to turn on the cooling system. Using this switch, you can either choose to control hydrogen production rate or the input current. I am going to choose the hydrogen production rate. This push button deblock this converter. You can see it turns to green color. Then we can connect the electrolyzer to the plant by closing this circuit breaker. I am going to do it by pressing this push button. It is going to trigger a plot update, which is going to take about 10 seconds. Once the plots are updated, I am going to open this first hierarchy box in orange color. It provides electrical waveform of the system. You can see that the plant current and the power input to the electrolyzer is increased to its operating values. The converter voltage is reduced to the operating voltage from its open circuit voltage. The firing angle of the converter is increased and set to about 35 degrees. In this hierarchy box, you can see all the plant waveform related to the hydrogen energy side. First, you can see the plant hydrogen and oxygen production rate in these two waveforms. Then you can see the stack temperature dynamics. Due to the start of the reaction, temperature is slightly increased but starting to come down. Typically, this stack temperature has large time constant, therefore it takes long time to settle in steady state. In this waveforms you can see the plant's water flow rate and the coolant flow rate. It shows how your controller adjusts the coolant flow to keep the temperature at 350 Kelvin. Finally, we have the tank variables. Since the hydrogen produced by the electrolyzer is stored inside the tank, you can see that the pressure, temperature and the internal mass of the tank is increasing. That is the end of this case. Now let's have a look at an advanced hydrogen system. Once the plots are updated, I am going to open the first hierarchy box in orange color. It provides electrical waveform of the system. You can see that the plant current and the power input to the electrolyzer is increased to its operating values. Converter voltage is reduced to the operating point voltage from its open circuit voltage. Firing angle of the converter is increased and set to about 35 degrees. In this hierarchy box, you can see all the plant's waveform related to the hydrogen energy side. First, you can see the plant hydrogen and oxygen production rates. Then you can see the stack temperature dynamics. Due to the start of the reaction, temperature is slightly increased but starting to come down to the desired value. This temperature dynamic has a large time constant. Then you can see the water input rate and the coolant flow rate to the plant. It shows how your controller adjusts the coolant flow rate to keep the temperature at 350 Kelvin. Finally, we have the tank variable. Since the hydrogen produced by the electrolyzer is stored inside the tank, you can see that the pressure, temperature and the internal mass of the tank is increasing. This is the end of the simulation case. Now let's have a look at an advanced hydrogen system. My next demonstration is a fuel cell power generation plant which generates power from stored hydrogen gas and feed to the grid. This system consists of a grid, a coupling transformer, power electronic interface and the fuel cell plant. Power electronic interface consists of a grid side converter and a DC to DC converter which is placed inside this fuel cell plant hierarchy box. Grid side converter controls the real power and the reactive power of the grid. As you can see, a decoupled controller is employed for this task. I am not going to go into the detail of this controller. Inside the fuel cell plant, you can see the DC to DC boost converter and the all other plant components. Fuel cell voltage is typically small, therefore a boost converter is used to step up and regulate the plant's output voltage to a desired DC value. A dual loop control scheme is used to control the boost converter. Outer loop of this scheme controls the output voltage of this system, that is the DC bus voltage. Inner loop of this controller controls the fuel cell current. This current control is required to prevent fuel cell from exceeding their maximum current density. Output of the control loop is the duty signal to generate the PWM switching for the boost converter. This plant consists of the fuel cell stack, which is placed inside this hierarchy box, and several other multi-energy flow components we developed for the hydrogen energy simulation. Each of these multi-energy flow components serves a specific objective for the operation of the plant. First, we have the storage tank. It provides the stored hydrogen gas to the fuel cell operation. Then there is the anode side compressor. It controls the pressure and the rate of the hydrogen gas that is given to the fuel cell. Flow mixture adds water to the fuel to maintain the humidity of the fuel cell's membrane. Then we have the cathode side compressor. which compress outside air and provide them to the cathode of the stack. Then plant also consists of several controllers and safety features. Cooling control system of the fuel cell is the same as the electrolyzer cooling system. It controls the coolant flow to the maintain fuel cell stack temperature. Humidity controller determine how much water need to be added to the fuel in order to keep the membrane humidity. You can see some background calculation to compute the molar fraction of each compound. Then we have the fuel controller that control the hydrogen and air flow rate to the anode and cathode of the fuel cell. This fuel controller first computes a current reference based on the power reference of the grid side converter. Then using this reference, current reference and the fuel utilization factor, it computes the hydrogen and oxygen requirement or the supply rate to the stack. In this case, I am using utilization factor of 0.7. Inside the hierarchy box named trip logic, you could see the safety and trip logic implement for the plant. At the top, there is the starvation detection system. It generates a plant trip signal if the fuel cell is starving for more than a given amount of time. Next one is the membrane's low humidity detection system. A dry membrane for a long period of time may damage the fuel cell. Therefore, the system must be shut down. Then in this side, you can see the hydrogen tank pressure monitoring system. It detects the low tank pressure, which means the tank is running out of fuel and the system must be shut down immediately. If the fuel cell voltage is too low, then it cannot feed power to the grid. Fuel cell's voltage monitoring system detects this scenario and generate a trip signal to shut down the plant. Based on the safety requirement of your system, users can add more protection features to the system. For each safety feature, if detected, it generates a trip signal that disconnects the fuel cell plant from the grid. Now let's move to the runtime of this case. In this case as well, we have runtime graphic to depict the system and the meters to monitor important quantities during the simulation. Sliders to change system and control parameters are placed inside the hierarchy boxes at the top. Runtime plots are included inside these hierarchy boxes at the bottom. Control references and settings can be changed using the sliders placed in the main runtime canvas. Let's run the simulation. After starting the simulation, I am going to follow the sequence. First, I press this push button to close circuit breakers of the electrical system. Then I am going to turn on fuel supply and the cooling system. And when I press this deblock button, it's going to deblock both converters and connect this circuit breaker. You can see circuit breaker turn into green color, which means the fuel cell is now connected to the grid. During the simulation, you can monitor these meters for real-time values. For example, you can see the power flow to the grid is 0.1 megawatt, which means 100 kilowatt, and the voltage is 1 per unit. So these values are matching with our control references. You can monitor the modulation index of the grid side converter and the duty ratio of the boost converter. DC voltage of the DC bus is controlled at 0.8 kV, 800 volts. You can monitor the fuel cell voltage, current and the power flow. If you go inside this hierarchy box, you can see the plant variable, flow properties and the component stats such as the mechanical power consumption of the compressor, stack temperature and the humidity level, and the tank pressure, mass and the temperature. Now I am going to give a disturbance to the system by changing the power reference to 0.5. It takes about 20 seconds to update the plots. While we are waiting, we can observe these values. Now you can see the power flow to the grid is changed to 0.05, which means 50 kilowatts. Voltage of the grid is still 1 per unit. DC voltage is not changed, but the current voltage and the power of the fuel cell have changed. Let's see the electrical waveform of the system first. As you can see from this plot, as the fuel cell adjusts to the new setting, their power output is cut in half, which leads to a drop in current as well. Because of this, the fuel cell output voltage goes up following its polarization curve. If you remember the fuel cell characteristic curve from the presentation, it had a negative slope. Even after the current stabilizes, the voltage keeps fluctuating due to the temperature dynamic of the stack. Apart from that, you can see that the change in power causes temporary fluctuation in both DC voltage and the AC voltage, but the controller quickly corrects these values and bring them to the set value. You can see the plant waveform inside this hierarchy box. As the fuel current drops as a result of the reference change, the consumption of hydrogen and oxygen also goes down. Fuel controller adjusts the fuel delivery rate to the stack to keep the utilization factor steady. This is why you are seeing this reduction of hydrogen and oxygen to the stack. As the reaction rate in the stack slows down due to the reduced power, the stack temperature initially drops slightly, but the temperature controller compensates by reducing the coolant flow to bring the temperature back to the desired value. It takes a longer time to come back due to the large time constant, as you can see in this waveform. This also caused the membrane humidity level to settle at a higher value after a brief drop. Meanwhile, the tank internal pressure, mass and the temperature steadily decrease as it releases gas for the fuel cell operation. If I go inside this hierarchy box, you can observe breaker signals and the control signals. Here you can see the duty of the boost converter and the modulation index of the grid side converter. Then inside this hierarchy box you will see the trip signal. Right now everything is at 0 and the plant is operating perfectly fine. This is the end of my demonstration. Thank you everyone for joining.
Thank you, Janesh. And thank you, everyone, for your attention during the presentation and your great questions. We have lots today. So I'm glad to see the interest in hydrogen modeling and HIL testing of controls. I'm going to start by just talking about one of the questions we had about the number of cores involved and how much simulation hardware is required to run these cases. So I believe most of the hydrogen sample cases we have in RSCAD Effects use 3 licensed cores of our NovaCore platform. And all of the new sample cases that we're developing, unfortunately, they are exclusively for so that means that if you're running PB5s, you might come across some limitations. These cases, of course, can be scaled down to a certain degree and certainly scaled up. With PB5s, you're going to have a more stringent node restrictions and definitely some restrictions on power electronics modeling. So that could potentially be a bit challenging. But if you're a user, feel free to contact us and we can help you adapt our sample cases for use on your PB5 racks. And these sample cases are located energy storage folder, which is number 5 in the library, as you might have seen from the demo. So feel free to explore them yourself. And the cases are documented, so they include the hardware allocation information at the top of the PDF document. Okay, so let's go to a couple questions about these models. Janesh, we have a question about whether the fuel cell is a static or dynamic model. Do you want to talk a little bit more about that?
Yes, thank you, Kathy. Yes, this fuel cell is a dynamic equivalent model because this equivalent circuit consists of ideal voltage source and 3 resistors to represent the cell. Each resistance and this voltage source are calculated in each time step. So the value for these resistances and voltages depend on the thermal and hydraulic variables such as the fuel availability, uh, the temperature, pressure, and other variables such as the starvation factor and other plant variables. So we calculate this equivalent circuit each time step. Therefore, it may vary during the simulation. So it's a dynamic equivalent circuit.
Yeah, thank you. And these models are running in the 25 to 50 microsecond range. So that gives you some idea of the rate of change. We have a question also about the coolant flow options for the fuel cell. So could you expand on that a little bit, Janesh?
Yes, this model is developed considering 2 types of coolant flows. First one is the water coolant and the second one is the air. If water option is selected, we consider it is 100% water. There is no gases in all. If air is selected, we consider it is 80% nitrogen and 20% oxygen. So based on those parameters, we calculate the thermodynamic properties.
Great,
Yes.
thank you. Okay, we're almost out of time, but we have a recent question on whether this software contributes to conducting a harmonic steady analysis at any hydrogen facility using PEM technology-based electrolyzers. So the short answer is yes, if I'm understanding the question correctly. You can definitely look at harmonics here. The bandwidth varies depending on the time step that you're using. So we have multi-rate simulation options with the RTDS simulator. So you can, for the power electronics specifically, you can run them in the main time step and look at frequencies in the 10 kilohertz range, or you can run them at a smaller time step and represent in the 150 kilohertz range. So you have a pretty wide range of bandwidth there to look at. Okay, we are just about at the top of the hour. Janesh, do you have any other comments?
there is a question related to temperature range, so I can answer that. So
Perfect.
it is the temperature range is selected based on the accuracy of the polynomial we use to calculate the thermodynamic properties of each gas and water. For hydrogen, the minimum is 62. For nitrogen, oxygen, it's 200 Kelvin, but depend on your mixture. So you can understand that the accuracy will change based on the temperature range of your simulation. So this is why we have given this minimum temperature, but it not necessary telling you to use that temperature for the simulation. It's the accuracy of the polynomial we use for the thermodynamic property calculation.
Okay, thank you. Great. So we are out of time, but thank you again, everyone, for attending. Please feel free to contact us if you have additional questions. If you watch this webinar on demand, you can still submit questions and we'll receive them by email. This example case, yes, is available in RSCAD 2. Actually, Janesh, are the cases available in 2.2 or just 2.4?
2.2 and above, yeah.
Perfect. So yes, you can download them in 2.2. Just noticed that question. Thank you, everyone. And again, you'll be redirected to our upcoming Applications and Technology Conference page when the webinar ends. And we hope to see you on our next webinar. Thank you so much, Janesh, for presenting today.
Thank you, Kathy, and thank you, everyone.
Great. Okay, have a great day, everyone.